The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
In the last lecture, we discussed discrete time processing of continuous time signals, and as you know, the basis for that arises essentially out of the sampling theorem. Now, in that context, and also in its own right, another important sampling issue is the sampling of discrete time signals. In other words, the sampling of a sequence. One common context in which this arises, for example, is if we've converted from a continuous time signal to a sequence, and we then carry out some additional filtering, then there's the possibility that we can resample that sequence, and as we'll see as we go through the discussion, save something in the way of storage or whatever. So discrete time sampling, as I indicated, has important application in a context referred to here, namely resampling after discrete time filtering. And closely related to that, as we'll indicate in this lecture, is the concept of using discrete time sampling for what's referred to as sampling rate conversion. And also closely associated with both of those ideas is a set of ideas that I'll bring up in today's lecture referred to as decimation and interpolation of discrete time signals or sequences. Now, the basic process for discrete time sampling is the same as it is for continuous time sampling. Namely, we can analyze it and set it up on the basis of multiplying or modulating a discrete time signal by an impulse train, the impulse train essentially, or pulse train, pulling out sequence values at the times that we want to sample. So the basic block diagram for the sampling process is to modulate or multiply the sequence that we want to sample by an impulse train, and here the impulse train has impulses spaced by integer multiples of capital N. This then becomes the sampling period. And the result of that modulation is then the sampled sequence x sub p of n. So if we just look at what a sequence and a sampled version of that sequence might look like, what we have here is an original sequence x of n, and then we have the sampling impulse train or sampling sequence. And it's the modulation or product of these two that gives us the sampled sequence x sub p of n. And so as you can see, multiplying this by this essentially pulls out of the original sequence sample values at the times that this pulse train is on. And of course here I've drawn this for the case where capital N, the sampling period, is equal to 3. Now, the analysis of discrete time sampling is very similar to the analysis of continuous time sampling. And let's just quickly look through the steps that are involved. We're modulating or multiplying in the time domain, and what that corresponds to in the frequency domain is a convolution. And so the spectrum of the sampled sequence is the periodic convolution of the spectrum of the sampling sequence and the spectrum of the sequence that we're sampling. And since the sampling sequence is an impulse train, As we know, the Fourier transform of an impulse train is itself an impulse train, and so this is the Fourier transform of the sampling sequence. And now, finally, the Fourier transform of the resulting sample sequence being the convolution of this with the Fourier transform of the sequence that we're sampling gives us then a spectrum which consists of a sum of replicated versions of the Fourier transform of the sequence that we're sampling. In other words, what we're doing, very much as we did in continuous time, is through the sampling process, when we look at it in the frequency domain, taking the spectrum of the sequence that we're sampling and shifting it and then adding it in, shifting it by integer multiples of the sampling frequency. In particular, looking back at this equation, what we recognize is that this term, k times 2 pi over capital N, is in fact an integer multiple of the sampling frequency. And the same thing is true here. This is k times omega sub s, where omega sub s, the sampling frequency, is 2 pi divided by capital N. All right, so now let's look at what this means pictorially or graphically in the frequency domain. And as you can imagine, since the analysis and algebra is similar to what happens in continuous time, we would expect the pictures to more or less be identical to what we've seen previously for continuous time, and indeed that's the case. So here we have the spectrum of the signal that we're sampling. This is its Fourier transform with an assumed highest frequency of omega sub m, highest frequency over a 2 pi range, or over a range of pi rather. And now the spectrum of the sampling signal is what I show below, which is an impulse train with impulses occurring at multiples, integer multiples of the sampling frequency. And then finally, the convolution of these two is simply this one replicated at the locations of these impulses, and so that's finally what I show below. And here I've made one particular choice for the sampling period. This in particular corresponds to a sampling period which is capital N equal to 3. And so the sampling frequency, omega sub s, is 2 pi divided by 3. All right, now when we look at this, what we recognize is that we have basically the same issue here as we had in continuous time, in the sense that when these individual replications of the Fourier transform, when the sampling frequency is chosen high enough so that they don't overlap, then we see the potential for being able to get one of them back. On the other hand, when they do overlap, then what we'll have is aliasing, in particular discrete time aliasing, much as we had continuous time aliasing in the continuous time case. Well, notice in this picture that what we have is we've chosen this picture so that omega sub s minus omega sub m is greater than omega sub m, or equivalently so that omega sub s is greater than 2 omega sub m. And so with omega sub s greater than 2 omega sub m, that corresponds to this picture, whereas if that condition is violated, then in fact the picture that we would have is a picture that looks like this. And in this picture, the individual replications of the Fourier transform of the original signal overlap, and we can no longer recover the Fourier transform of the original signal. And this, just as it was in continuous time, is referred to as aliasing. Now, let's look more closely at the situation in which there is no aliasing. And So in that case, what we have is a Fourier transform for the sampled signal, which is, as I indicated here, and the Fourier transform for the original signal, as I indicate at the top. And the question now is, how do we recover this one from this one? Well, the way that we do that, just as we did in a continuous time case, is by low-pass filtering. In particular, processing in the time domain or in the frequency domain. This, with an ideal low-pass filter, has the effect of extracting that part of the spectrum that, in fact, we identify with the original signal that we began with. So what we see, again, is that the process is very much the same. As long as there's no aliasing, we can recover the original signal by ideal low-pass filtering. So the overall system is, just to reiterate, a system which consists of modulating the original sequence with a pulse train or impulse train, and then that is going to be processed with a low-pass filter. The spectrum of the original signal x of n is what I show here. The spectrum of the sampled signal, where I'm drawing the picture on the assumption that the sampling period is 3, is now what's indicated, where these are replicated, where the original spectrum is replicated. This is now processed through a filter which, for exact reconstruction, is an ideal low-pass filter. And so we would multiply this spectrum by this one, and the result after doing that will generate a reconstructed spectrum which in fact is identical to the original. So the time domain picture is the same. I'm sorry, the frequency domain picture is the same, and what we would expect then is that the time domain picture would be the same. Well, let's in fact look in the time domain, and in the time domain what we have is an analysis more or less identical to what we had in continuous time. We of course have the same system, and in the time domain we are multiplying by an impulse train. Consequently, the sampled sequence is an impulse train whose values are samples of x of n at integer multiples of capital N. For the reconstruction, this is now processed through an ideal low-pass filter, and that implements a convolution in the time domain. And so the reconstructed signal is the convolution of the sampled sequence and the filter impulse response, and expressed another way, namely writing out the convolution as a sum, we have this expression. And so it says then that the reconstruction is carried out by replacing the impulses here, these impulses, by versions of the filter impulse response. Well, if the filter is an ideal low-pass filter, then that corresponds in the time domain to a sine nx over sine x kind of function, and that is the interpolation in between the samples to do the reconstruction. Also, as is discussed somewhat in the text, we can consider other kinds of interpolation. For example, discrete time zero-order hold or discrete time first-order hold, just as we had in continuous time. And the issues and analysis for the discrete time zero-order hold and first-order hold are very similar to what they were in continuous time. The zero-order hold, just simply holding the value until the next sampling instant, and the first-order hold carrying out linear interpolation in between the samples. Now, in this sampling process, if we look again at the waveforms involved, or sequences involved, the process consisted of taking a sequence and extracting from it individual values, and in between those values we have sequence values equal to 0. So what we're doing in this case is retaining the same number of sequence values and simply setting some number of them equal to 0. Well, let's say, for example, that we want to carry out sampling, and what we're talking about is a sequence, and let's say the sequence is stored in a computer memory. As you can imagine, the notion of sampling it and actually replacing some of the values by 0 is somewhat inefficient. Namely, it doesn't make sense to think of storing in the memory a lot of zeros when in fact those are zeros that we can always put back in. We know exactly what the values are, and if we know what the sampling rate was in discrete time, then we would know when and how to put the zeros back in. So actually, in discrete time sampling, what we've talked about so far is really only one part or one step in the process. Basically, the other step is to take those zeros and just throw them away, because we can put them in any time we want to, and really only retain, for example, in our computer memory or list of sequence values or whatever, only retain the non-zero values. So that process and the resulting sequence that we end up with is associated with a concept called decimation. What I mean by decimation is very simple. What we're doing is, instead of working with this sequence, we're going to work with this sequence. Namely, we'll toss out the zeros in between here and collapse the sequence down only to the sequence values that are associated with the original x of n. Now, in talking about a decimation,